Momentum, the most fundamental property in physics. Once an object is moving, it stays moving, unless something acts on it. This principle has never failed, never been violated, never shown exceptions in billions of observations across 4 centuries of celestial mechanics. Until now, 3I Atlas, the interstellar comet traveling through our solar system at over 30 kilometers per second, is slowing down. Not drifting slightly off course, not showing minor trajectory adjustments, slowing, decelerating, losing velocity in ways that gravitational forces alone cannot explain. Multiple observatories tracking the comet have reported the same finding independently. The object is arriving at predicted positions later than calculations say it should. Initially, just minutes behind predicted timing later, the cumulative delay reached measurable hours across multiple observation windows. Something is acting against 3I Atlas motion. Something is removing momentum from an object that should be coasting freely through interplanetary space. And the mechanisms responsible don't fit any standard model of cometary physics. NASA has not issued formal statements declaring this a priority anomaly, but observing schedules have been adjusted. Data sharing between institutions has intensified, because when an interstellar visitor demonstrates behavior that challenges our understanding of how objects move through space, the implications extend far beyond one comet. This is the story of an object that came from beyond our solar system and decided that momentum conservation is more like a suggestion than a law. Understanding how astronomers detected the slowdown requires understanding the precision of modern positional astronomy. When observatories measure a comet's location against background stars, they achieve accuracy measured in fractions of an arcsecond. That's angular precision equivalent to resolving a coin from several kilometers away. These measurements, repeated nightly across weeks and months, build an astrometric data set. Each position measurement gets time-stamped precisely. Each observation records exactly where the comet appeared at exactly what time. Orbital mechanics allows prediction of future positions with extraordinary accuracy. Given enough initial observations to calculate the orbit, equations tell us where any object should be at any future moment. For 3I Atlas, with its well-characterized hyperbolic trajectory, those predictions should be rock solid. But starting in late October 2025, discrepancies appeared. 3I Atlas wasn't arriving at predicted positions when predicted. The comet appeared slightly behind where calculations said it should be. Not dramatically, not by amounts visible to casual observation, but measurably, consistently, repeatedly. At first, observers assumed measurement uncertainty or systematic errors in the observations. Telescopes get recalibrated, reference star positions get checked, timing systems get verified. Every possible source of error gets scrutinized. The discrepancies remained, and they showed a pattern. The comet wasn't randomly scattered around predicted positions. It was systematically lagging, arriving late, traveling slower than pure gravitational trajectory predicts. By early November, the accumulated positional data made the conclusion inescapable. 3I Atlas is decelerating. Something is removing kinetic energy from its motion. Something is acting like a brake. This is profoundly strange. Objects in space don't just slow down. There's no friction, no air resistance, no medium to create drag. Once moving, objects continue moving at constant velocity unless forces act on them. And the only significant force acting on comets at this distance from the Sun should be gravity, which curves their paths but doesn't remove energy from their motion along that path. Yet 3I Atlas is slowing, measurably, significantly, inexplicably. Subscribe now, because understanding what's causing this deceleration might reveal natural processes we've never directly observed before. The first explanation scientists propose for any unexpected cometary motion is outgassing. Jets of gas and dust venting from the nucleus can create thrust accelerating or decelerating the comet depending on jet orientation relative to the direction of motion. For most comets, outgassing creates acceleration. Jets preferentially vent from the sunward side where solar heating is strongest. As the comet rotates, these jets sweep around, and their average effect tends to push the comet slightly faster along its orbit or slightly off the predicted gravitational path. But jets can also create deceleration if oriented correctly. If active regions vent primarily from the forward-facing side of the nucleus, if gas escapes in directions opposite to the comet's motion, the rocket effect works in reverse. The comet loses momentum. It slows down. This is rare but not unprecedented in solar system comets. A few objects have shown similar behavior. Comet Encke, for instance, experiences orbital decay partially attributed to non-gravitational forces that slow its motion. So could outgassing explain 3I Atlas deceleration? Perhaps, but the details don't match expectations. Imaging shows 3I Atlas has an active coma. Material is clearly being released. Jets are visible in high-resolution images, appearing as spiral streamers characteristic of rotating nuclei with localized active regions. But spectroscopic measurements of gas production rates don't indicate activity levels sufficient to explain the observed deceleration. To slow an object traveling at 30+ kilometers per second by measurable amounts requires releasing substantial mass at high velocity in specific directions. The spectroscopy suggests moderate activity, not the vigorous outgassing that deceleration of this magnitude should require. There's a fundamental mismatch. The trajectory says strong braking. The spectroscopy says modest activity. These observations need reconciliation. One possibility, 3I Atlas is venting species that are difficult to detect spectroscopically. Carbon monoxide, for instance, is harder to observe than water vapor in optical wavelengths, but can be abundant in comets. If the comet is releasing large amounts of carbon monoxide or other volatiles that our spectroscopy isn't fully capturing, the actual gas production could be much higher than measurements suggest. Another possibility, the jets are oriented in particularly effective configurations for creating deceleration. Even modest gas production, if concentrated in forward-facing jets that vent directly opposite the direction of motion, could create disproportionate braking effect. But both possibilities require specific conditions that seem convenient explanations rather than predictions from first principles. We're adjusting our models to fit observations rather than observations confirming independent predictions. Understanding outgassing thrust requires knowing how the comet rotates. Rotation rate and axis orientation determine which parts of the surface face the sun at which times, which affects where active regions develop, and what directions jets point. For 3I Atlas, rotation remains poorly constrained. Light curve analysis, which tracks brightness variations caused by rotation, shows complex patterns. The brightness doesn't vary smoothly and periodically as expected from a simple rotating ellipsoid. Instead, it fluctuates irregularly, suggesting either highly irregular shape, non-uniform surface properties, or both. Extracting a definitive rotation period from this noisy data has proven challenging. Different analysis techniques yield different results. Some suggest rotation periods of hours. Others indicate days. The uncertainty is large enough that modeling jet behavior becomes highly assumption dependent. Without knowing rotation precisely, predicting how jets create net force requires guessing. We assume rotation rates. We assume active region locations. We assume jet orientation. And then we calculate whether those assumptions can produce the observed deceleration. This approach can make almost any observation fit almost any model by adjusting assumptions. It's scientifically unsatisfying. We want observations that constrain models, not models that we adjust until they fit observations. The rotation uncertainty also affects how we interpret the deceleration itself. If 3I Atlas rotates rapidly, jets sweep through many orientations quickly, and their average effect should be easier to predict. If it rotates slowly, jets maintain orientations longer, potentially creating sustained thrust or drag in specific directions. Comment below. If you could observe 3I Atlas with any instrument, what measurement would you prioritize to solve this mystery? Internal structure profoundly affects cometary behavior. But for 3I Atlas, we can only infer structure indirectly from surface observations. Comets range from relatively cohesive bodies with significant structural strength to loosely bound rubble piles barely held together by weak self-gravity and ice acting as frozen glue. These structural extremes respond very differently to solar heating. A cohesive comet with low porosity conducts heat slowly. Solar radiation heats the surface but doesn't penetrate deep quickly. Sublimation remains confined to surface layers. Activity is steady and predictable. A rubble pile comet with high porosity allows heat to penetrate rapidly through voids and cracks. Solar energy reaches subsurface ice deposits that haven't been processed by previous solar passages. These deposits sublimate vigorously when heated, creating sudden outbursts and irregular activity. If 3I Atlas is a rubble pile, its response to solar heating might be fundamentally different from typical solar system comets. Internal voids could trap sublimated gas, building pressure that vents explosively through weak points in the structure. These episodic releases could create impulsive forces that significantly alter trajectory in ways steady outgassing cannot. Evidence for rubble pile structure might include irregular brightness variations, sudden outbursts, or fragmentation events. 3I Atlas does show some irregular brightness behavior, but whether that indicates rubble pile structure or simply surface heterogeneity remains unclear. Fragmentation would provide strong evidence of weak structural integrity. If pieces are breaking away from the main nucleus, if the comet is actively disintegrating under thermal stress, the dynamics become far more complex. Mass loss from fragmentation creates momentum changes that can decelerate the parent body. And if fragments separate asymmetrically, the remaining nucleus experiences net force that alters its trajectory unpredictably. Have observers detected fragmentation? The evidence is ambiguous. Some images show elongation or multiple brightness peaks that could indicate separated fragments, but resolution limits prevent definitive confirmation. At 3I Atlas distance, even large telescopes can't resolve individual fragments unless they separate by substantial distances. The structure question remains open, and without knowing whether we're observing a cohesive nucleus or a fragmenting rubble pile, modeling the forces causing deceleration becomes highly speculative. Predictably, 3I Atlas' unusual behavior has spawned speculation about artificial origin. Online discussions propose that the deceleration indicates powered braking, active navigation, or controlled descent into the inner solar system. Let me state this unambiguously. There is zero credible evidence supporting artificial origin. No radio signals detected, no geometric structures observed, no propulsion signatures measured. Every observation is consistent with natural cometary processes, even if we don't yet understand which specific processes are operating. The speculation arises because 3I Atlas combines interstellar origin with unusual behavior, the same combination that sparked controversy around 1I Oumuamua. But unusual doesn't mean artificial. It means our models, built on studying objects from one star system, might not perfectly predict behavior of objects from different stellar environments with different formation histories. Science requires evidence. Artificial origin requires demonstrating design, technology, intentionality. We haven't even fully characterized the natural explanations yet. Outgassing, rotation effects, structural properties, fragmentation all remain partially constrained. Until we've exhausted natural explanations, invoking artificial ones is premature at best and actively misleading at worst. The deceleration is real. The cause is uncertain. But uncertain doesn't mean inexplicable by physics. It means more data is needed, better models are required, and patience is essential while scientists work through rigorous analysis. Understanding 3I Atlas deceleration has practical implications beyond satisfying scientific curiosity. It matters for how we model interstellar objects generally and how we might respond to future visitors. If interstellar comets routinely show non-gravitational forces stronger or more complex than solar system comets, trajectory predictions become more uncertain. That uncertainty affects mission planning for any spacecraft attempting intercepts. It affects risk assessment if hazardous interstellar objects are ever discovered. It affects our basic understanding of small body dynamics in the galaxy. Currently, planetary defense models assume objects follow predictable gravitational orbits with well-characterized non-gravitational perturbations. If 3I Atlas demonstrates that interstellar visitors can show deceleration beyond standard outgassing models, those assumptions need revision. This doesn't mean 3I Atlas poses any threat. Its trajectory passes safely through the inner solar system with no Earth impact risk. But it demonstrates that interstellar objects can behave unpredictably in ways that complicate trajectory forecasting. For future missions attempting to study interstellar visitors up close, understanding these non-gravitational forces becomes crucial. Rendezvous trajectories require precise predictions of where the target will be. If the target is decelerating unpredictably, rendezvous becomes significantly more challenging. 3I Atlas is teaching us these lessons without stakes. No mission is currently trying to intercept it. No impact threat exists. We can study its unusual behavior purely for scientific understanding, building knowledge that will inform future encounters when stakes might be higher. Solving the deceleration mystery requires sustained observation across multiple wavelengths using diverse techniques. Astrometry continues tracking positions nightly. Each measurement refines understanding of how velocity is changing. Is the deceleration constant, accelerating, episodic? The pattern will constrain possible mechanisms. Spectroscopy measures gas production rates across multiple molecular species. By identifying what's being released and in what quantities, astronomers can estimate total outgassing rates and whether those rates suffice to explain observed deceleration. Infrared observations track thermal emission from the nucleus and coma. Temperature measurements constrain how much solar energy is being absorbed and how that energy drives sublimation. Radio telescopes search for molecules like carbon monoxide that optical spectroscopy might miss. If significant carbon monoxide is present, it could explain why visible wavelength measurements underestimate total gas production. High-resolution imaging attempts to detect fragmentation or resolve jet structures. Understanding where material is being released and in what directions is crucial for modeling thrust forces. All this data feeds into models that attempt to reproduce observed behavior. Researchers input measured parameters, make assumptions about unknown quantities like rotation rate and structure, calculate expected forces and resulting trajectory changes, then compare predictions to observations. When models match observations, we've successfully explained the phenomenon. When they don't, we know assumptions are wrong and iterate toward better models. This process takes time. Months of observations accumulating, careful analysis, checking for systematic errors, multiple independent research groups cross-validating results, peer review before publication. But gradually, the explanation will emerge. Natural processes operating in unusual configurations that we haven't observed before. New understanding of how comets from different stellar environments behave under solar heating. Expanded physics that encompasses both familiar solar system objects and exotic interstellar visitors. As I record this, 3I Atlas continues its deceleration, continues arriving late to predicted positions, continues demonstrating that objects from other star systems don't necessarily follow the rules we've written based on local experience. This is science confronting its limits. We thought we understood cometary motion. We've studied thousands of comets. We've sent spacecraft to several. We've built comprehensive models that work beautifully for solar system objects. Then an interstellar visitor arrives and shows us our models are incomplete. Not wrong, not useless, but incomplete. Adequate for the environment where we develop them, but insufficient for objects formed under different conditions around different stars. The deceleration will be explained. Natural processes we haven't fully characterized yet. Outgassing configurations we haven't modeled. Structural properties we haven't encountered. Combinations of factors that produce outcomes our simplified models don't predict. What it certainly isn't is artificial. Not because artificial is impossible, but because we haven't exhausted natural explanation. Science demands we explore ordinary possibilities before invoking extraordinary ones. 3. IATLAS is slowing down. Scientists admit they don't have complete explanations yet, and that admission isn't weakness, it's honesty. It's the foundation of discovery. Because every time we encounter something we don't fully understand, every time observations challenge our models, every time we're forced to admit uncertainty, we're positioned to learn something new, to expand our understanding, to build better frameworks that encompass more of reality's complexity. The comet that slowed down is teaching us that the universe is more subtle, more varied, more surprising than our theories capture. And the data being collected right now, the observations accumulating nightly, the measurements constraining possible mechanisms, all of it is building toward explanations that will improve how we understand not just 3I Atlas, but every interstellar object we'll encounter in the future. Comment below. What natural mechanism do you think is most likely causing the deceleration? And subscribe. Because this mystery is still unfolding, observations continue, and as scientists work toward answers, we'll bring you updates on what they discover about this unpredictable visitor from beyond our solar system. The comet that slowed down is still being watched. The physics is still being worked out. And somewhere in the data being collected right now, the answer is waiting to be found.